Hey everyone, welcome back to Multi-Agent Reinforcement Learning Series. Today is Lesson 4, and today is where rubber meets the road, diving into real-world complexities. We've been exploring MARL in idealized environments, kind of like learning to drive in a simulator. But today we are getting our hands dirty with the messy, unpredictable challenges that emerge when we deploy MA systems in real world. This is where things get really interesting. And first, kudos to everyone for those fantastic student representations, and you are thinking about real problems that really need multi-agent solutions. Now let's quickly recap. In our previous lessons, we explored the self-paced autocurriculum where agents learn by competing against themselves, and centralized critics with the CTD paradigm that allows agents to use the global information during training while maintaining decentralized execution, and mean field theory for handling thousands of agents by modeling the population as a continuous distribution. But here's the honest truth. We made general assumptions. We assumed fully observability, that agents can see everything. We assumed free communication, that agents can exchange unlimited information instantly. And we assumed perfect behavior, that nothing breaks and no one cheats. Well, there's an alert. The real world is far from perfect. So what's our mission today? We are embracing the mess. 3 major technical challenges: partial observability, communication, robustness, and safety. Now let's dive in. So our first challenge is partial observability, or the fog of war. This is the most fundamental gap between the textbook algorithm and reality. In our previous discussions, we worked with Markov decision processes where agents see the true state. But think about real scenarios. Robots navigating buildings only see what their sensor detect, okay? And cars in traffic only observe nearby vehicles, and trading algorithms only access to limited market data. So do they really know the complete state? Of course not. Okay, we're dealing with POMDPs, partially observable Markov decision processes. Here's the difference. Fully observability is like playing chess where you can see the entire board, every piece laid out clearly. But partial observability is like driving in a thick fog. You see a few meters ahead and catch glimpses of the car in front, but you are constantly inferring what's beyond your vision from indirect clues, a horn, a vibration, or brake lights, right? The mathematical formulation is simple but profound. The observation at time step t is not equals to the true state. Instead, observations are sampled from a distribution that depends on the state and previous actions. Yet, agents must make optimal decisions anyway. And this introduces the fundamental uncertainty that agents must learn to manage. So how do we solve this? Let's start with memory. If one observation isn't enough, we can use a history of observations to infer the state. Think about seeing someone smile. Without context, you don't know why. But if you remember hearing laughter 5 minutes ago and seeing them receiving a gift, and suddenly it makes sense. We give agents this capability using recurrent neural networks, especially LSTM or GRU cells. Here's how it works. At each time step, the agent receives an observation and updates its hidden state. This hidden state becomes the agent's belief state, a compressed representation summarizing everything relevant it has seen. The LSTM has 3 gates working together: a forget gate, deciding what old information to discard, and an input gate, deciding what new information to store, and an output gate, deciding what to expose for decision making. So the beauty is that through backpropagation through time, the LSTM learns exactly what to remember and what to forget. For example, in a navigation task, it might remember the location of a goal seen 100 steps ago while forgetting an irrelevant obstacle that have since moved. Okay, let me give you a concrete architecture. In a deep recurrent queue network, which we call DRQN, we can replace the standard DQN's fully connected layer with an LSTM. First, we extract features from raw observation using a CNN, and then we process these features through an LSTM to update the belief state. And finally, we output actions values based on the belief state. The key difference from standard DQN is that we train on a sequences of experiences rather than individual transitions. Okay, this requires strong trajectory. This requires storing trajectory in the replay buffer, not just the single transitions, which increases memory requirement but provides the temporal context necessary for learning under partial observability. Okay, the loss function sums over the entire sequence, allowing gradients to flow backward through time and teach the LSTM what patterns matter for predicting the future rewards. Okay. Now the second solution, attention, which means that not all information is equally important. So let's learn to focus on what matters. Imagine you're at a busy party with dozens of conversations. Your brain filters automatically, focusing on the person speaking to you while the background chatter fades. Okay, the attention mechanisms give agents this kind of selective focus. Consider a soccer player surrounded by the teammates, opponents, and the ball and field marking. A defender might focus 80% attention on the opponent with the ball and 15% on nearby attackers, and 5% on everything else. These weights are learned dynamically through training. Okay? And mathematically, for an agent observing multiple entities, we compute three things. A query representing what the agent is looking for, keys representing what each entity offers, and values representing the actual information. So the attention weights are computed by comparing a query with all keys using a dot product and normalized through a softmax function. Then we aggregated information by taking the weighted sum of the values. Okay, so the agent then makes decisions based on the context-enriched representation. It's like having a smart filter that automatically highlights the most relevant information while dimming the noise. Okay, now here's a practical design question. Should agents attend globally to all others or only locally within a radius? There's no universal answer, actually. In swarm robotics with thousands of drones, maybe global attention creates computational complexity that grows quadratically within the number of agents, which is prohibitive. But in small tactical teams with 5 to 10 agents, global attention might provide crucial long-range coordination signals. For example, a scout agent detecting an enemy should immediately alert all teammates, not just nearby ones. And this design choice depends on team size, computational budget, and task requirements. It's always about a trade-off. Okay, now let me bring this to life with Hanabi, a cooperative card game. Players must play cards in ascending order, 1 through 5 for each color. The twist is you can see everyone else's card but not your own hand. You are making decisions about which card to play without knowing what you are holding. So the only way to figure out your hand is through limited hints from teammates. For example, you have one red card, or this card is a 4. Hints are precious. You only have 8 hints tokens for the entire game. So the agent must use memory to integrate the entire history of actions and hints. Did someone hint about red cards 3 turns ago? Did another player discard a red 4, meaning your meaning yours might be safe to play. So every piece of information is a clue, and the agent builds a belief or probability distribution over which card it likely holds, right? Mathematically, this is a Bayesian belief updating. So the probability of holding a particular hand given the entire history equals the likelihood of that history given that hand times the prior probability of that hand divided by the overall probability of observing that history. And the LSTM implicitly learns this Bayesian update through training and tracking complex dependencies across dozens of time steps. Okay, and state-of-the-art Hanabi agents using this approach achieve near-perfect scores, sometimes even outperforming human expert players. It's remarkable to see an agent reason through such complex hidden information just by learning from experience. Okay, here's a quick engagement check. In partial observability scenarios, what's the main advantage of using LSTM memory? Type A for fast computation, type B for belief about hidden states, or C for reducing the training time. 3, 2, 1. Excellent. Lot of B's. Absolutely right. It's about building belief about hidden states by integrating information over time. Okay, now let's shift to our second challenge, communication, the art and science of talking. The central question is, can agents learn to talk? Not follow the pre-programmed protocols, but invent their own language from scratch. The solution is differentiable communication, pioneered by systems like DIAL, which stands for Differentiable Inter-Agent Learning. The key insight is make the communication channel part of the end-to-end learning. Here's the architecture. Agent 1 creates a message and sends it to Agent 2. Agent 2 incorporates that message into its observation and takes actions. When Agent 2 receives a reward, greetings flow backward through its policy, but here's the magic. They continue backward through the message itself to Agent 1's message creation policy. So Agent 1 gets direct feedback on whether its message helped or harmed the team objective. Over time, agents develop highly efficient communication protocols without any human supervision or predefined vocabulary. Okay? But here's where it gets arrayed. The resulting languages are often completely alien to humans. Messages might be continuous vectors in high-dimensional spaces. Imagine communicating through colors in 2, 5, 6-dimensional space. Totally uninterpretable to us, okay? Or they might be used discrete symbols, but in ways that seems arbitrary. Okay, for example, in one experiment with navigation text, agent developed a communication protocol where message 372 meant I'm heading north, obstacle at grid B4, you go around east, but there's no semantic connection between those numbers and the meaning. It's purely learned association that works for the agent but makes no sense to us. Okay, it's like eavesdropping on dolphins. We know they are communicating because we see the communication improve dramatically with communication enabled versus disabled. Okay, but the structure, the grammar, and the semantics are opaque. So this raises fascinating questions about the nature of language and meaning in artificial systems. Are we witnessing the emergence of truly alien forms of communication? So that's a question. Now let's do the reality check. Okay, communication is not free. Okay, real system face bandwidth limitation, network latency, energy consumption, and in adversarial setting, communication can be intercepted or jammed. This leads to practical solutions. First, selective communication with gating mechanisms that learn when messages are worth sending. During training, agents learn that trivial information doesn't warrant messages, while critical events always trigger communication. Second, message compression using autoencoders. Agents learn to compress maximal information into minimal bits, like compressing a 1024-dimensional state vector into a 34 dimensions while preserving task-relevant information. Okay. Third is hierarchical coordination for large teams. A manager sets high-level goals like worker A secure north entrance, worker B scout ahead, and workers execute with low-level actions. This dramatically reduces communication burden because you are coordinating intentions, not actions. Okay, instead of broadcasting every movement command, the manager sends secure trains once and the worker figured out the action sequence. It's like basketball coach who sets plays but does not micromanage every dribble. Okay? Now consider a collaborative air traffic control. Multiple AI controllers manage crowded airspace, each responsible for a different sector. When aircraft cross boundaries, here's a handoff requiring critical information: call sign, altitude, speed, heading, destination, and so on. But agents can't broadcast everything constantly. That would overwhelm channel. So they need structured, targeted message at precisely at right time. Okay, the challenge has 3 dimensions: what to communicate, when to communicate, and whom to communicate with. Okay. With learned communication protocols, agents discover through training that handoff message should be sent exactly 2 minutes before the boundary crossing, with essential information like predicted position and velocity. Emergence situations trigger broadcast to all sectors, okay, while routine operations use targeted messages. Right? The resulting system can surpass hard-coded roles because it adapts to specific patterns. For example, learning that certain sectors have congestion during evening hours and proactively coordinating to distribute the load. And this is not just theoretical. There are active research projects with aviation authorities showing enormous potential benefits. Now we have a quick question. For warehouse robots moving packages, should they use all-to-all communication or selective communication? Type 1 for all-to-all, type 2 for selective. Okay, 3, 2, 1, great. Mostly 2s. The practical choice. With dozens or hundreds of robots, all-to-all creates massive overhead. Imagine 100 robots where each broadcasting every second. That's a lot of messages per second. And selective communication, broadcasting only when detecting obstacles or requesting help, is far more scalable, right? Okay, our third critical challenge is robustness and safety, surviving in hostile, high-stake worlds. We've been assuming benign environment, but the real world is messier and sometimes hostile. We face 2 main threats. The first is noise, like sensor errors, action failures, communication drop-offs. A robot will slips, a camera gets obscured, and packages get lost. This isn't adversarial, they are just natural reliabilities, okay? The second is adversaries. Malicious agents actively disrupting your team and think cyber attack, sending false information or adversarial perturbations, confusing autonomous vehicles, like specifically designed stickers that makes a stop sign look like a speed limit sign. So our defenses comes into 2 forms. For noise, we use domain randomization during training, injecting random variations to force agents to learn robust policies. And instead of memorizing exact positions, agents learn approximate strategies with feedback-based adjustment. Okay, and for adversaries, we use adversarial training where a second agent tries to make your team fail. It's a minimax game where the adversary found worst case attacks where your team learns to counter them. this arms race during training produces resilient agent at deployment. Okay, but robustness is not very enough. In autonomous driving, medical planning, or infrastructure control, we cannot afford catastrophic failures. Like a self-driving car that is faster but occasionally runs red light is unacceptable. The problem with standard reinforcement learning is that agents learn through exploration, trying all actions including unsafe ones. In simulation, that's fine, but in reality, we can't afford a single catastrophic failure. Okay, the solution is safety layers of shielding. We train a high-performance but potentially unsafe RL policy in simulation and then combine it with a formally verified conservative policy as a shield. Okay, the safety layer monitors intended actions. If safe, execute as planned. If potentially violating constraints, the shield intervenes with a safe feedback. Okay, the safety policy is formally verified with mathematical proof that it satisfies safety constraint. One approach uses control barrier functions defining a safe set. For a self-driving car, this might represent minimum distance to obstacles, ensuring the car never gets closer than some threshold even in RL policy. Yeah, and we get the best of both the worlds. The RL policy can be creative and optimized because the safety layer catches mistakes, while the safety layer guarantees the critical constraints are never violated. So this is crucial in multi-agent systems, where one agent's unsafe action could cascade into team-wide failure. Okay? Now let me tie all these three challenges together with a smart grid control. AI agent control power generators and distributors across a region, meet demand and preventing blackouts and minimizing cost. For partial observability, no single agent has complete grid information, and agents use LSTM memory to track temporal patterns like demand spikes at 6 p.m., so ramp up at 5:45. They use attention to focus on critical measurements like frequency deviations, and for communication, agents must coordinate under bandwidth constraints. They use selective communication where emergency messages get high priority while routine updates are sent less frequently. And hierarchical coordination within regional coordinators reduces the complexity dramatically. And for safety, this is hostile. High-stakes environment with unpredictable demand spikes, encryption failures, and potential cyber attacks. Like the 2015 Ukraine power grid attack shows these threats are real. And the critical constraint is maintaining frequency with narrow margins, and these threats are real. Yeah. So if frequency drifts outside, the proactive displays connected parts of grid. So cascading into citywide blocks or blackouts affecting hospital and emergency services. The integrated solution uses memory, attention for state inference, alert communication for coordination, and domain randomization and adversarial training for robustness, and a safety shield that overrides any command potentially pushing frequency outside the safe bound. Research groups are deploying these techniques in pilot programming, showing 10 to 15% efficiency improvement with perfect safety records. Okay. The final question: in smart grid control, what's most critical for deployment? Type A for efficient communication, B for handling partial observability, and C for safety guarantees. Okay, 3-1, lot of C's, and I completely agree. While all three are essential, safety guarantees are non-negotiable. You can tolerate some inefficiency and suboptimal decisions, but you absolutely cannot tolerate citywide blackouts. So the safety layer is the foundation everything else builds on. Okay, now we come to your homework. Your homework is to solve a PLMDP using memory. Okay, we're using a modified Python zoo environment where we've removed velocity information from observations, creating meaningful partial observability. First, run the provided memory-less baseline and document its performance. Does it move erratically? How does coordination look? Okay, second, implement DRQN by adding an LSTM layer. And the architecture flows from observation through embedding through LSTM to Q values. Third, train your DRQN and compare against the baseline. Look at the performance metrics and behavior analysis with trajectory visualization. And fourth, write a brief report analyzing what the LSTM learns. Okay, the hands-on exercise builds deep intuition about memory-based architectures and why they are essential for real-world partial observability. Okay, now let's synthesize our journey. Our theme has been bridging theory and practice. Challenge 1, partial observability. We explored LSTM memory networks, building belief state attention mechanisms, focusing on relevant information, and Hanabi demonstrating belief building and DRQN architecture. And for challenge 2, communication, we covered differentiable communication, enabled end-to-end learning, selective communication, handling bandwidth constraints, and hierarchical coordination for scaling and air traffic control showing structured communication. And for the challenge 3, robust and safety, we examined domain randomization for noisy and adversarial training for defense, and safety layer providing formal guarantees and smart grid control integrating all challenges. Okay, so next up, lesson 5. Future horizons, the vast potential of MAI, and we will explore the cutting edge and the beyond. Okay, so these are the all of these are the frontiers defining next generation multi-agent system. The future is incredibly exciting, and we are right at the beginning of this transformation. So that wraps up today's extended lesson. For the fog of partial observability to learning communication protocols to ensuring safety in deployment, we've covered substantial ground. Thank you for your excellent engagement with these interactive questions. Your participation makes this much more dynamic and helps me to gauge whether these concepts are landing. So don't forget the homework challenge. Implementing DRQN will give you hands-on experience with memory-based architectures that's invaluable for understanding these concepts today. And theory is one thing, but when you see your own agents learn to remember and use the history effectively, that's when it really clicks. Okay, so don't forget, next time is Future Horizons. We'll explore where this field is heading and the transformative potential of multi-agent AI. And see you then. Okay, bye-bye, take care.